In this problem, I will talk about the process of finding the gravitational force that an extended object, an object with a mass density, exerts on a point particle. And I will talk about the process that you can use in general to find those kind of gravitational forces. You do know from introductory physics how to calculate the gravitational force between two point particles. The most simple model that we use in physics, 2 point particles. Now, what I will show you here is how to extend that approach, how to use that force between 2 point particles to calculate the gravitational force in this case, where I have a rod on the z-axis. This rod is lying on the z-axis and it has a uniform mass density, and I have a point particle at this location, a distance rho from the rod. Now, for the rod, I will use, as I said, I will set the uniform mass density. I'm going to use the Greek letter mi for that. This is the mass density. The units will be the mass per unit length. Okay, that's why I call it the mass density. If it was, and this is a linear. Okay, this is a linear mass density. And it is linear because my object is simply one dimensional. Okay, that's why I'm using the linear. It is mass because I have mass in the numerator, and I'm gonna use this quantity in my calculations. Now, my point particle is located here. This is with a yellow color, and this is the position of this point particle. Now, I am using cylindrical coordinates right now. And the reason why I'm going with cylindrical coordinates is because the rod is lying on the z-axis. So it is important for me to keep the z-axis. Now that means I have two choices between Cartesian and cylindrical because both of them include the z-axis. Now, since the point particle is located distance rho from the origin, what is really important for me is the distance from the origin to the point particle. It doesn't matter to me whether the point particle, whether this point mass is on the x-axis, on the y-axis, or neither of the two. The important thing is to have the distance from the origin, and this is telling me that I can start by using the cylindrical coordinate system and then see where that takes me. Now, I'm gonna give you an overview. We do know, so the gravitational force between 2 point particles is given by minus the gravitational constant m1, m2. If I'm interested in finding the force that one exerts on two, then this will be the r vector from 1 to 2, the magnitude squared times r hat, where r hat is the unit vector from 1 to 2. This is the gravitational force between 2 point particles. Now, I don't have 2 point particles, so what do? The process I'm going to use is the following. I will say I'm going to choose an arbitrary piece from that rod. Okay, an arbitrary piece means that it's not going to be on a specific point. It's going to be at some arbitrary location that will be the 0, 0, z. Okay. If in this case, if here you were saying I'm gonna choose my small mass to be located at the origin, the origin is not an arbitrary location. It has to be somewhere that is not a specific point. And the 0, 0, z is the position vector of that small mass. I'm gonna call it delta m. Now, what I'm gonna do, the approximation that I will use is that, well, I would say since, okay, the whole rod is obviously not a point particle, but since I'm only looking at a small piece from that rod, I will make the approximation that this small piece, exerts a gravitational force on the point particle that can be calculated by this. So in essence, I'm modeling this small piece of mass as a point particle. Now, is it really a point particle? The answer is no, it's not. However, the smaller I make this piece, the closer, the better my approximation becomes, and the more accurate my results will be. So I'm getting there. For now, I'm just treating it as a point particle, even though it's not. It's a small piece of mass. So what I'm gonna do now, I will go ahead and calculate the vector r that goes from 1 to 2. Now, in this case, what is 1 and what is 2? I'm gonna change my notation. So 1 is the delta m, the small piece of mass. And I'm interested in finding the force that the small piece of mass exerts on the point particle. And this will be the position of the point particle minus the position of the small piece of mass. And this is the rho 0, 0 minus 0, 0, z. And this will be rho 0 minus z. Now, the next thing I need in this expression is the magnitude. And the magnitude is calculated as the square root of each component, the sum of each component squared. The minus will go away since I'm only looking at the square. And then the unit vector is calculated as the vector over the magnitude. And what this gives me is rho, comma 0, comma minus z with the distance. Now that I have everything, I will combine it into this expression. So that will give me the gravitational force from the small piece of mass to the point particle minus g m delta m, the magnitude squared, so that will be simply rho squared plus z squared, and then times the unit vector, but the unit vector in the denominator includes the square root. So what I can do here is say that this is simply 3 over 2 rho 0 minus z. Now here I want to talk about how I got the 3 over 2. When I do the magnitude squared as I have in the expression, this will give me essentially 2 over 2. Okay, the square root will go away, so 2 over 2 equals 1. But then in the denominator of r hat that I need to use here, I do have a 1 over 2. So 2 over 2 plus 1 over 2 will give me 3 over 2. And I'm writing it this way because it's a little bit more simple. Now I can change, let me change my vector notation. Minus g m delta m, I have rho squared plus z squared 3/2. I'm just switching notation. Now what I found is the gravitational force that a small piece of mass exerts on the point particle. Since I have a rod that extends from the negative z-axis to the positive z-axis, what I need to do is really calculate the same expression from all the small pieces that I can think of. So for example, this would be here one small piece, another small piece, another small piece, and so on. You can think of dividing the rod into many small pieces like the one I just used here. And then I'm calculating from each small piece, I'm modeling them as a point particle, and I'm finding this force. And then what I need to do, since I'm looking for the force from the rod, from the entire rod on the point particle, I need to add all of those forces that are coming from all of these small pieces. So adding them means I need to find the sum. And I am moving on. Let's separate. So moving on. No. So the force from the entire rod on the point particle will have to be the sum now I'm gonna say delta m sub I, so it's gonna be the sum of all of those forces. So this will be the sum, and now I'm using the result that I found before, g m delta m sub I rho squared plus z squared, this is to the power of 3/2. Now, this expression will give me the gravitational force from the entire rod. As I said though before, my calculation will be more accurate the smaller those pieces are. And the best I can do is cut the rod into an infinite number of pieces that are infinitely small. So essentially what I'm going to do is I'm going to take the limit, say, so I will go from 1 to n. Here I'm gonna add that I'm making this the limit when n goes to infinity, because this will make my calculation more accurate. But we do know when you divide things into infinitely small pieces and you take the limit when n goes to infinity, in this case, I'm really converting the sum into an integral. So my expression is going to look like this. Fg from the rod on the mass. This is going to be an integral of minus gm. Now the delta m, the delta that I used with the sum, now that I'm using an integral, this will become dm. And everything else stays the same. I will move on so that I can figure out what I'm gonna do with this integral. Now, as you saw in my integration, I have a dm. I know that the rod has a uniform mass, linear mass density of me, and I said before the units of that are kilograms over meters. Now, I need to see what I'm gonna do with the dm. One way that I can use this linear mass density is the following. Since in the numerator I have kilograms and here I have meters, I can say, well, this linear mass density for an infinitely small piece will simply be dm over dz. Okay, it is an infinitely small piece, and I have a mass of dm, and the length of it is dz, since the rod lies on the z-axis, and dm over dz will give me the linear mass density. Now, what I have in the integral is dm, so the way to solve for dm, I'm gonna do me, the mass density, times dz. And now I'm gonna go back to my integral and see what I get when I do that. So my gravitational force from the rod on the point particle was the integral minus g m, and I said dm is going to be me times dz, and I had rho squared plus z squared to the power of 3 over 2. That was rho times rho hat minus z hat. Now here is where I have to set the limits of the integration. Since I know that the rod extends from minus infinity to plus infinity, this means I'm integrating from minus infinity to plus infinity. Z, since that's my variable of integration, z will need to go from minus infinity to plus infinity because the entire rod is infinite. Now, I can look at some constants here. G is a constant, of course, minus is a constant, m is a constant, the linear mass density is a constant because it's a uniform rod. And then the only thing that I have is the rest, so I can take my constants out of the integral. Now, this integral can be broken into two, and I will show you how. So I will have minus g m times me, and let's do bracket So what do we have left? We have rho is a constant actually, but that constant I have it only in this component, so it will be rho dz rho squared plus z squared to the power of 3 over 2. Now this is going to be multiplied with rho hat, and then I have why do I have the minus sign? I think I don't need the minus sign here since I took it out of the integral, but I do need a minus sign here with z going from minus infinity to plus infinity, and what I have is z dz rho squared plus z squared 3 over 2 times z hat. All right, so what I did essentially, I got rid of the bracket here, and now I have, this will give me the rho hat component, and this will give me the z hat component. I will I will let you do the calculations for these two integrals. So the two integrals that you will need to find is really rho, but rho is a constant, and I can still leave it here. Rho dz rho squared plus z squared 3 over 2. So you need to do this calculation, and you also need to do this calculation. Z dz rho squared plus z squared 3 over 2. So you need to find those two integrals, and those two will tell you the two components. Now, I will give you a hint though that can help you find out if you have a mistake or not. Since this is a uniformly a rod with a uniform mass, density, then I do have an expectation. If there was more mass on this side, I would be expecting the force to be pointing that way. If I had more mass on this side, I would be expecting the force to have a component in this direction. What I do know is that there is the same amount of mass from both sides of the origin on the z-axis. So this is telling you something about the z component. Now, let's take a look at the integrals. These are the two integrals you have to find. There are, at least I would say, I am familiar with two ways or maybe three, to find the integrals. One way will be to you remember the methodology from your calculus class, and you move on and you do it. If you can remember how to do these kind of integrals. The other approach would be to look up the integral in a book that has mathematical expressions, and in particular in this case integrals, and do some pattern matching and see what is the result of this integral, and then do the same thing for this one, and that will give you the two integrals that you need. Or if you're familiar with Mathematica, you can Mathematica can do some integration for you, and then you just use the result here. Either whatever way you choose is fine with me. Now this is going to give you the gravitational force from the rod on the mass. Now this force, I want to talk about one more thing. Since I am using the cylindrical coordinate system, then the three coordinates I'm using are rho, phi, and z. Okay, the distance from the origin, the angle from the positive x-axis, and then z is of course the z-axis. Now the force that you will have when you do those integrals, the force that you will have from the rod on the mass will be written in terms of rho, phi, and z. And of course, the force may not depend on some of these coordinates, and that's fine. That's actually even better if you have if you don't have much dependence on the coordinates. Now, if you want to prove that this is 0, then since I am using the cylindrical coordinate system to write the force, the easiest way to do it would be, of course, to find the expression for the curl in cylindrical coordinates. Now, do I remember what this looks like? I don't. And I never remember what this looks like. What I do, if I need the curl in cylindrical coordinates, I look up a book and I copy down the expression, and then I do the calculations for the curl. Now, there is another thing that you can do. You can calculate, of course, the curl of a vector in a different coordinate system. So you can use Cartesian. But then, if you do want to use the curl in the Cartesian coordinate system, what this means is that you need to transform the force that you have written in cylindrical coordinates. You need to transform that to a vector, the force vector, that is written in terms of the Cartesian coordinates. And now, how to do that? What I need to do, do I remember how to do this transformation? I don't. And again, whenever I need to do that, I'm going to look up in a book, and I'm gonna find, of course, z is gonna be z. What I will find is, I will have three equations. On the left side, I will have this will be my cylindrical coordinates. And then on the right side, I will have an expression that includes x and y. And the same thing here, x and y. And this is the right side. This right side will only be written in terms of the Cartesian coordinates. And once you find these expressions, what you do, you replace every rho, every phi, every zeta, every z with a corresponding expression from here, from these three, and then at the end you will end up having your gravitational force written using the Cartesian coordinates.